We are talking about subgroups of a group. If G is a group, a subset H of G is called a subgroup of G. If H forms a group in its own right with the group law and the identity element borrowed from the group G. And we use this notation H less than or equal to G. We gave some examples. Let me make introduce a couple more words. If you have a subset A of a group G, you say that A is closed under multiplication if whenever A and B, little a and little b is in capital A, then the product A times B is also in capital A. So the product of two things in A is again in A. And you say that A is closed under inversion if whenever you have an element in A, its inverse is also in A. And then we have this recognition principle for a subgroup. If you have a group G and H is a subset, then H is a subgroup if and only if it contains the identity and it's closed under multiplication and inversion. So it was written in words, in formulas last time. Now we have introduced the two words. And then there's a third condition which is almost similar. Yeah, but you can check these conditions given in part 2 or part 3 to figure out whether something is a subgroup or not. So what we want to talk about now is certain subgroups in terms of generators. So we want to talk about generators and relations a little bit. Generators. For a group and for a subgroup. So G is always going to be a group. Maybe first we'll start with an exercise. This is very straightforward. Let's just have a fixed group to begin with. G be a group. Then we won't have to write it again and again. Intersection of a family of subgroups, collection, let's say, of a collection of subgroups of G is again a subgroup of G. So it's saying that if you have two subgroups, then their intersection is again a subgroup. If you have 5 subgroups, their intersection is again a subgroup. If you have countably many, still the same thing. If you have any arbitrary collection, the intersection is still a subgroup. That's why I say it in words, because I am not saying that there are countably many or anything. There could be any number of them. Finite, infinite, as many as you want. And the proof of this exercise is just straightforward from this lemma on the left. You just check these 3 conditions, that the intersection again satisfies these conditions given in the lemma part 2. So if you have a bunch of subgroups in a group G, the common part is again a subgroup. Okay. That's what you want to remember. So, if you give me any subset of G, I can find the smallest subgroup containing it. So let S be a non-empty, let's say, empty subset of G. Then let, I'm going to denote by angle bracket X, be the intersection of all the subgroups of G that contain S. And there is such a subgroup after all. There is one subgroup that contains S. G itself is a subgroup of G, you see. and G certainly contains S. So this collection of subgroups that contain S is non-empty. So if I intersect them all, I again get a subgroup. And this subgroup, which I denote by angle bracket S, is pretty much by definition the smallest subgroup that contain S. So verify that this is the smallest subgroup of G that contain S. It's a subgroup because of the exercise, because I'm intersecting a bunch of subgroups. And each of them contain S, so this guy also contains S. And because I'm intersecting all the subgroups that contain S, this is the smallest one. Okay, we call that this is the subgroup of G generated by S. And we say S is a set of generator for this. So if H is a subgroup of G, we say that S is a set of generators, or a generating set, generators of H, or that S generates H if H is angle bracket S. And then I'll give you another exercise. This is rather straightforward. What are all the things that are in angle bracket S? So if S is a finite set like this, A1, A2, I don't even have to take finitely many things, I suppose. But I want to introduce a little notation here. If S is a finite set like this, we'll write this as just angle bracket A1, A2, AN. Okay. So now, what are all the things in angle bracket S? If you have a bunch of things in S, then this subgroup is going to contain them, so they are going to contain all their powers, all sorts of products like this, AI1, AI2, AIK, where these AI1, AI2, AIK are from here, their inverses, etc. And if you take all such expressions, then you see that that forms a subgroup, so that must be angle bracket S. So that's what the content of this next lemma is. Lemma. Let S be a non-empty subset of G, then angle bracket S consists of all things like this: A1 to the I1, AN to the IN, where A1, A2, AN in S, and I1, I2, IN are integers. And if you don't have anything, then the empty product means the identity. Okay. So all such products of elements of S, all finite products. And you can take positive powers, negative powers. Yeah. So in particular, each A in G generates a cyclic group, angle bracket A, which is just all powers of this element. We say that this is the cyclic group generated by A. We say we're not claiming that all the A to the n's are distinct. They may not be. Yeah, so this is sort of why cyclic groups crop up everywhere. If you give me any group and any element in there, just take all its power, that's going to be a subgroup. And these are like little simple subgroups that sit inside G, and how they sort of sit in capital G's often helps in understanding the structure of capital G. So let me give you some examples of a few maybe. Well, Z is generated by 1, also generated by -1, because if you take all multiples of 1, you get Z. Meaning if you think of a subgroup of Z that contains 1. If it contains 1, it also has to contain 1 plus 1. It also has to contain 1 plus 1 plus 1, etc. It has to contain all the positives. But if it contains 1, it also has to contain its inverse, so -1. So -1, which is -2, etc. And then 1 minus 1, it's 0, so that also it has to contain. If you just take the subgroup generated by, let's say, I don't know, 4 and 6, you're not going to get all of Z. But if you take all the subgroup, all the smallest subgroup containing 6 and maybe 11, then you're going to see all of Z. So the condition, same for, I don't know. So you can check that a bunch of numbers are going to generate Z if and only if their GCD is 1. So if you take all multiples of 4 plus all multiples of 6, that's what this subgroup is going to contain. And that's actually all multiples of 2. That's a subgroup of Z, you can check. That's not the whole of Z. Okay? If you take, for example, so we say 4, 6, this is a set of generators for 2Z. Well, 2 is also a generator. So same subgroup can have plenty of generators. Another one. This is a rather important one. If you take these permutations, this is the permutation that in cycle notation is just written as 1, 2. It's like 4 letters. And then and then this one. So the first one switches 1 and 2 and leaves everything else intact. The second one switches 2 and 3. The third one switches 3 and 4. So these are 3 elements of, let's call them sigma 1, sigma 2, sigma 3. These guys are elements of S4. And they generate S4, you can check. This is a rather nice set of generators for